Welcome back, Marauders. This video, 8.8, Strength of Covalent Bonds. We're going to be looking at what bond strength means and then how to calculate the enthalpy change of a reaction based on average bond enthalpies. So the strength of a bond is basically how much energy it takes to break it. And so we can measure that in kilojoules per mole typically. And another way of thinking about that is bond enthalpy. So remember, enthalpy is your energy change, and it's the amount of energy that it takes to break a bond. Breaking a bond is going to require energy, so you'll have to put energy in to break a bond. And then the opposite of that, forming a new bond, is going to have the opposite enthalpy change, so it'll give you energy back. It will release energy. The strength of a bond can be estimated based on how many pairs of electrons you have shared. So single bonds are the weakest, double bonds are stronger because you have more electrons being shared, and triple bonds are the strongest. It's also going to depend what type of elements you have bonded together. But if you have the same two elements, triple bonds are always stronger than double, which are always stronger than single. And then it's inversely related to the bond length. So triple bonds are the shortest bonds, and they're the strongest. Single bonds are the longest and the weakest. So we can find the enthalpy change of a reaction using average bond enthalpies. Average bond enthalpies will be provided for you on a test, or you can look them up in the back of a book or some other index. And energy is required to break bonds. So that's going to be your positive part. You're going to have to put energy in to break bonds. And then energy is going to be released when new bonds are formed. So that's your exothermic part. We're basically using Hess's law. We're assuming that all the bonds are going to be broken. So we're seeing how much energy it takes to break all those bonds. And then we're forming all new bonds. So how much energy are we going to release back? And the difference between those will be the overall enthalpy change for the reaction. So you will be able to look up the bond enthalpies either in your book or it'll be given to you on a test. And then the enthalpy change of the reaction is the energy it takes to break all the bonds minus the energy released when all the new bonds are formed. So another way of writing that, enthalpy change overall of the reaction is equal to the sum of all the enthalpies to break bond enthalpies to break all the bonds minus the bond enthalpies for all the new bonds that are formed. So the type of question that you'll typically see could be something like this, where we're trying to find the bond enthalpy, the enthalpy change for this reaction. So we're trying to find delta H. We've done that in earlier chapters using calorimetry or enthalpies of formation. Bond enthalpy is a little bit different. So the first thing we need to do is draw Lewis dot structures for these so we know what types of bonds we're dealing with. So in CH4, you have a carbon in the center, and then you have single bonds to 4 hydrogens. So we'll draw the Lewis dot structure for that so we can see what bonds are going to need to be broken. We have 2 oxygens. It's important to draw this Lewis dot structure out so you can remember that oxygen has a double bond. We're going to draw this twice because we have 2 oxygens. So we have 2 molecules of oxygen. Each oxygen molecule has a double bond between the 2 oxygens. On my product side, I have 2 waters. So waters would be drawn like that for its Lewis dot structure. We'll draw it twice since we have 2 of them on our product side. And then we have a CO2, carbon dioxide. So carbon dioxide has double bonds between the carbon and the oxygen. So you need to draw out the Lewis dot structures so you know what types of bonds you have and how many of each one you have. All right, so now what we need to do is add up all the energy to break the bonds. So the bonds that need to be broken are these. So we're going to be breaking 1, 2, 3, 4 bonds between carbon and hydrogen. So we'll look up the bond enthalpy for a carbon to hydrogen bond, and it's 413 kilojoules per mole. We have 4 of those, 1, 2, 3, 4. So it's going to be 4 times 413. So that's the energy to break all of these bonds. And then plus what other bonds need to be broken on our reactant side. We have oxygen to oxygen double bonds. We have 1, 2 of those. So we're going to be breaking 2 bonds of oxygen to oxygen. Now there's 2 different types of oxygen bonds. You can have an oxygen single bond, which is 146, or an oxygen to oxygen double bond, which is 495. Notice that the double bond is stronger, but it's not always exactly double the strength of the single bond. So make sure you look up the correct type of bond. That's why it was important to draw the Lewis dot structures at the beginning. So we have 2 double bonds, so 2 times 495. And so those bonds are all going to need to be broken on our reactant side. And then the bonds that are going to be formed, the bonds that are going to be exothermic, giving us energy back, so that part's going to be negative, will be 1, 2, 3, 4 bonds between oxygen and hydrogen. So we have 4 bonds that are 467. Plus we have carbon to oxygen double bonds. We have 1, 2 of those. So that's 2 times 799. And then we take the difference there and you get negative 824 kilojoules. So the enthalpy change for this reaction is 824 kilojoules. So remember, the steps are to draw out the Lewis dot structure so that you can see how many bonds you have and what type of bond you have. All the bonds that need to be broken, that part's going to be positive because it takes energy to break those bonds. That part's endothermic. And then the exothermic part, the part that's negative, is all the new bonds that are formed, because when new bonds are formed, energy is going to be released.